and gentlemen, my name's John Spink. I'm the head of the Crops, Environment and Land Use Programme in Teagasc, and I'd like to thank you for joining us today for the launch of the new Ammonia Marginal Abatement Cost Curve, or MACC. This morning, speaking to you, we have Professor Gerry Boyle, Director of Teagasc, Dr. Dominika Kroll, who's an environmental researcher in our Johnstown Castle Research Centre, and Dr. Cathal Buckley, who's an economist in our Rural Economy Programme. We have quite a lot of time at the end of the presentation. We're trying to keep the presentation short to allow plenty of time for questions and answers, which you can enter using the Q&A tab at the bottom of your screen, and we will deal with those at the end of the presentations. So I think without further ado, I'd like to hand over to Professor Gerry Boyle, who will now launch the new Ammonia MACC.
Thanks, John, and good morning, everyone. I'm delighted to see so many people tuning in this morning for this important event. As John said, I'm Director of Teagasc, and I'm very happy to launch this report today on the abatement of ammonia emissions. It's edited by my colleagues Dominika Kroll and Cathal Buckley, and it's very much a collective effort of the Teagasc Gaseous Emissions Working Group, which comprises of researchers and knowledge transfer colleagues, advisors and specialists from right across the organisation. And I guess the first question that's going to be addressed today, which is of huge importance, is why are we so concerned about ammonia emissions? Well, the first and primary concern is that it's a potent contributor to air pollution. And therefore, it's an emission that's of concern not just to farmers, but also to wider society. Secondly, Ireland has made several international commitments to reduce ammonia emissions. We have stringent targets to reduce emissions by 5% by 2030 relative to 2005. And again, if you look at a series of policy positions that have emanated from the European Union in recent times, such as the Green Deal, Farm to Fork, they all have stressed the importance of reducing emissions of both greenhouse gases and ammonia. And it's important to understand, and I don't think it's widely appreciated, that ammonia is quite a separate and distinct gas from the greenhouse gases that have been, of course, much in the public domain over the last number of years. I don't think the same appreciation exists in relation to ammonia, and hopefully today's event is going to clarify the importance of treating ammonia as a separate type of emission. Fortunately, many of the solutions overlap in terms of greenhouse gases and ammonia. Another impulse to focusing on ammonia emissions is, of course, the programme for government. And in development, we have a new strategy for 2030 being prepared by the Department of Agriculture, Food and the Marine. And again, it's important to appreciate the fact that there is also a very strong market pressure to address ammonia emissions. Why is it so important to agriculture? Well, one of the points that's going to emerge from today is that almost the entire level of ammonia emissions, 99% in fact, emanate from agriculture. And another interesting feature is that many of the solutions, if not most of them, concern pasture management. And that represents a challenge to us because 90% of our utilizable agricultural area, of course, is accounted for by permanent pasture. So today's marginal abatement cost curve is very much about providing solutions. you will see from the presentations later on this morning that about half of the measures, I think there are 13 or 14 measures in total that are set out in today's document, about half of them will actually add to farmer profitability. That's a very, very important message for us all to communicate to farmers. And another key point that comes out of today's analysis is that 80% of the mitigation potential as far as ammonia is concerned comprise two measures: the replacement of calcium ammonium nitrate by protected urea, and the use of what we call less technology, in other words, low emission slurry spreading technology. And I think those two factors together provide grounds for optimism that the sector will be enabled to respond and address the solutions that will help us to achieve our national targets by 2030. So with that, I'm really looking forward to a very good seminar. And what's most important is that we all, working collectively, strive to address the challenge of ammonia emissions by moving rapidly forward to implementation with our farmer stakeholders. Thank you, and back to you, John.
Thank you, Professor Boyle. I will now hand over to Dominica and Cathal, who will go into a little bit more detail about some of the items that the director mentioned there, and they will tell you a little bit of background about ammonia emissions, how the MACC analysis was done, and what the overall conclusions or findings of the analysis were. I think I'm handing over to you first, Dominica, if that's correct.
Yes, thank you very much, John. Now let me share my screen. Okay. Now, hopefully you should be able to see it very soon. Sorry, just bear with me to get it into the, yeah, slideshow mode. That's perfect. Okay. Now, so thank you very much for the overview, John and Professor Boyle. So yes, between myself and Cathal, we'll give you a bit of an overview of the new ammonia marginal abatement cost curve. Sorry, let me just, I'm just trying to get these. I'm afraid that might be the only thing I can do now. So hopefully that's not too distracting, guys. So at the very beginning, I'd like to acknowledge our co-authors from the Gaseous Emissions Working Group in Teagasc, and then myself and Cathal are the editors of this document. Okay. So the way the presentation will work today is between myself and Cathal. We'll share the slides and we'll talk you through a number of topics. So we'll start with the importance of ammonia, why we're interested in it at all, and what's the challenge with it. Then we'll move on to the MACC methodology. So we'll talk you through the emission factors and activity data in particular. Then we'll walk you through an example of how an implementation of one of the abatement pathways can work. And then we'll move on to results to the whole document, so all the measures all together. And then we'll give you a bit of an overview of what the impact of that mitigation could be on the national emissions profile. Okay, so we'll start with an importance of ammonia. And yes, it's it is an agricultural issue in terms that 99% of ammonia is produced by agriculture. Why it's of importance? Well, it can cause negative impacts on animal and human health and also on ecosystems. And it is regulated by two pieces of EU legislation, one being the National Emission Ceilings Directive, otherwise called NEC. And what we know about it is, so this legislation governs the allowable levels of emissions for the country. And then the other piece of legislation is Habitats Directive, which governs the allowable concentrations of ambient ammonia in the air. In terms of first emissions, what you can see is the historical profile of ammonia in Ireland. So what you can see is data from 1990 all the way to 2018, which is the most recent data available to us. So between 1990 to 1998, emissions were increasing, and then they pretty much steadily decreased all the way to 2011. And then they started on an upward trend again. So basically what it is they track animal numbers quite closely. And you can see that in terms of sources, it's a lot of it to do with animals and animal agriculture. Now, in terms of then concentrations, what you can see here is a recent paper from Callaghan et al. Showing concentrations of ammonia in Ireland. So this graph shows, this map shows a MARSH index, and MARSH stands for Mapping Ammonia Risk on Sensitive Habitats. So what you can see here is the lowest risk in the west of Ireland, and higher risk moving on to the east and south of Ireland. And it's also worth noting that in comparison, you can actually see a much worse situation in the north of the island of Ireland. So Northern Ireland seems to be getting it worse than we are. So on the backdrop of that, what's the challenge with ammonia emissions? Well, I've mentioned the NEC directive. We've actually been in breach of the NEC directive since 2016, and that's our current target. However, there are new targets coming in soon, which will be even more stringent and even more difficult to achieve. So from this year, we've a target of 1% reduction in ammonia relative to 2005. That's for the 2020 commitment period. And then that will move on to 5% reduction relative to 2005 from 2030 onwards. So as you can see, we're already breaching our current targets, and our new targets will be more stringent. So there is an urgent need for mitigation for ammonia emissions. And just to recap where the ammonia emissions are coming from in agriculture, here is a simplified breakdown of the sources of ammonia. So you can see that 3/4 of it is really to do with manure management, such as housing, storage, and land spreading of manure. The following 12% comes from grazing, and that's really, again, animal excreta just deposited at pasture. And the last 10% comes from synthetic nitrogen fertiliser. So these are really the sources that we need to tackle in order to reduce ammonia. And this has already been picking up by the national press. So the EPA had a press release saying that, well, Ireland's air pollutants are going in the wrong direction, and our ammonia emissions are on the rise. And the popular press has picked up on it as well. So this is a huge issue within Ireland. So that's the backdrop of the need for mitigation, and that moves us on to the methodology of the MACC and how the analysis was carried out. So firstly, MACC stands for marginal abatement cost curve. So it's a certain benchmarking analysis in which we can compare a number of mitigation, or otherwise called abatement, options for ammonia emissions. The way it is done is we calculate emissions and see how we can reduce those emissions. So the emissions are calculated using two pieces, one being activity data. So meaning, for example, how much fertiliser is spread, how much slurry is spread, and that's multiplied by emission factor. An emission factor is a percentage of nitrogen that is lost as ammonia in any given activity. For activity data, we are relying on the FAPRI model because we're looking into the future to 2030. So we're modeling activity levels in a number of scenarios. On the emission factors, we use the same ones as the ones used by the EPA in the National Inventory Model. So the EPA every year records and produces a report on the national emissions of ammonia and other air pollutants. So as a baseline, we use the emission factors used in that report. So firstly, we'll talk through emission factors, and then we'll move on to the activity data. So on the emission factors, they are all outlined in Chapter 4 for each individual measure. So you can see exactly where we're coming from and how the mitigation is working for each measure. The way the mitigation works is there is a certain emission factor associated with the baseline, so what's used in the EPA report, versus what we would like to achieve in the mitigation, so lowering that emission factor. So to give you an example, thinking about, for example, slurry spreading. If you spread slurry on a grassland in the summer, if you use splash plate, which is typically reported in the EPA report, that is associated with nearly 50% loss of ammonia from the available nitrogen in that slurry. However, if you move to trailing shoe, those emissions will be just at below 20%. So there's a huge reduction there. And as you can see from the slide, you can barely even see that slurry being spread on the grassland. Now, to give you another example of a synthetic fertiliser, again, not all fertilisers are the same, and they're associated with different emissions. So if you look at urea, there's approximately 15% of ammonia emission associated with spreading of that fertiliser. However, if we move from urea to what's called protected urea formulations, those emissions are going down to just over 3%. So there's a huge reduction there. Now you can also see that CAN is associated with less than 1% ammonia emissions. So there is a differential there. So you could ask me why we're not switching urea for CAN, because that really reduces emissions very, very powerfully. The issue is that we know CAN is associated with high emissions of a potent greenhouse gas, nitrous oxide. So we definitely don't want to fix one environmental issue and at the same time exacerbate another one. So we need to work on synergistic solutions here. So based on those, on the improvement in emission factors, so technologies that reduce those emissions, we came up with a total of 13 measures that were taken into the final MACC analysis. And they're all category 1 measures. So what this means is within ammonia mitigation measures, there's 3 general categories, where category 1 is that kind of most research, more practicable solutions that can be easily implemented. So that's what we're focusing on here. And what we have here is a menu of 13 measures. They're divided into 4 categories. So on the fertiliser side, we have protected urea, we've liming and clover. And protected urea is the largest measure here, and it follows the adoption pathway outlined in the draft acclimatise document. On the bovine side, we've 4 measures here that they're low emission slurry spreading, and again, this mitigation measure follow adoption pathway outlined in the draft acclimatise document. We also have reduction of crude protein in dairy cow feeds, covering of currently uncovered slurry stores, and adding slurry amendments. Then we've a carbon copy of those measures on the pig side, so another 4 measures. And lastly, we have 2 additional measures on the poultry side, and that being drying of poultry manure and adding slurry or manure amendments. Okay, and with that, that rounds up the emission factors. And I'll pass you on to Cathal now, who will be able to talk you through the activity levels.
Thanks, Dominica. So as Dominica has said, look, overall aggregate emissions are a function of activity levels by emission factor. So I'm going to focus on the activity levels here. So essentially, we've used the FAPRI Ireland model, or the output from the FAPRI Ireland model, run by Kevin Hanlon and Trevor Donlan. It's a partial equilibrium model of Irish agriculture. So they impose different scenarios, policy scenarios, in terms of to see what the level of overall agricultural activity would be in the country. So in the analysis, we've come up with 3 scenarios: S1, S2, and S3. They range from a business as usual, a lower activity scenario, and a higher activity scenario. So this is beneficial from a sensitivity analysis perspective. So you can see as the activity level varies, what happens to emissions. So starting with the first S1. The S1 scenario is kind of a more or less a business as usual scenario. The 2 main, I suppose, policy drivers here are CAP and Brexit. So under the S1 scenario, we're assuming that there's no real change under the CAP reform, and that we have a soft Brexit. Trade between the Ireland and UK is maintained pretty much as is, and then we're getting that more or less a historic, like, business as usual, steady state view of the world. The second scenario, activity level scenario, is S2, which is a lower level activity. So again, we're assuming no real change under CAP, but in this case, it's a hard Brexit. As we all know, hard Brexit is going to have a fairly big impact on Irish agriculture, particularly on the beef sector, and that's reflected in the overall activity level. Finally, then we have an S3 scenario, which is a higher level activity scenario. And this essentially is a soft Brexit. We also, under CAP, there's a coupling there's a direct payment coupled to suckler cows. So there's an incentive there for farmers to keep suckler cows. So this would kind of mean that suckler cow levels would kind of be higher than they would under the S1 or S2, because there's an incentive to keep them. So that's kind of how we keep how we impose a higher level activity level in S3. So what does that mean in terms of animal numbers? So the S1 is the dark green, the S2 is the light green, and the S3 is the orange. So you can see, because of the profitability of dairy cows, under all 3 scenarios, dairy cows tend to increase, but to varying degrees, and S3 being the highest. Conversely, under all 3 scenarios, activity level scenarios, the suckler cow numbers decline, but again, to various levels. Because of the coupled payment there, S3 have higher levels of suckler cow numbers, whereas the impact of Brexit is most severe on S2. And the suckler cow numbers and the dairy cow numbers drive the overall beef inventories in terms of calves that come from the national herd. So when you combine those 2, you get the overall. It tends to lead to the overall total bovine number. So under S2, you're getting a decline because of the decline in beef due to the hard Brexit is offsetting the increase in dairying. In the S1, you're getting a slight increase or slight decrease, because the beef is kind of offsetting the dairy, and essentially it's more or less a status quo. Whereas the S3, you're getting an increase because the activity levels are higher in the beef side and not offsetting the increase in dairy numbers. What does that do for overall fertiliser? Well, as the dairy cow sector tends to drive more the fertiliser inputs, because dairy requires more fertiliser to grow more grass. Under the S2, it's a slight decline. Under the S1, it's an increase, and under the S3, it's a bigger increase. So essentially, the dairy cow numbers are driving the increase in the overall chemical fertiliser under these projections. Okay, so when we plug in those activity level scenarios and we run them through the EPA, the National Inventory Model of the EPA, as Dominique has outlined earlier, we get the overall aggregate emission levels. And the 2 dots there are our net directive targets in 2020 and 2030. And as Dominique has said, we've been in breach of the net directive since 2016. And if those activity level scenarios come to pass and there's no mitigation, we're getting further and further away from our net directive target in 2030, as the diagram clearly illustrates. So that, I suppose, reinforces the need for mitigation. So again, I'm going to take you through an example of one of the measures to show you how we've outlined it and how we've modeled it, so you get a better understanding of where we're coming from. So all the measures in section 4, we've gone into huge detail in terms of how we model it. So, you know, we're not hiding anything. We're upfront about our assumptions. All the measures are set out in the same sequence and same format. So I'm just going to go through this format now using the example of protected urea. So we start out with a description. So in this case, we're following the acclimatized pathway where protected urea substituted for straight urea and CAN. We outline a table of results at the very top, and this table of results gives you the abatement in 2030 at the start and the cost in 2030. Why do we do that? Well, some of the measures don't get implemented until the very end of the study period, so you're not getting the full impact until the very end. So we like to show the average versus the full impact at the end. Column 3 and 4 give you the average abatement over the study period, 2021 to 2030, and the average cost. And when you combine the average abatement, average cost, you get a cost effectiveness ratio, which essentially is a measure of how cost effective the measure is to achieve reductions in ammonia. Then we go through the rationale. So essentially we're outlining the scientific basis for the mitigation pathway, the scientific studies that back up the reduction in emissions. Then we go through the assumptions. So what assumptions we've adopted in the mitigation pathway. So in this case, protected urea, it's the acclimatized proposal, and the cost differential is based on different quantities of fertiliser and the price of different fertilizers. Finally, then, penultimately, we look at how the mitigation pathway is reflected in the national inventory accounting. How do we get credit? If we're going to do this, how do we get credit for it? So in this case, it's through sales receipts. So we know the Department of Agriculture track fertiliser sales. So we know if the profile of sales is changing from CAN and straight urea to protected urea. That's how we get credit for it. And finally, then we look at any barriers to uptake. So are there kind of constraints there? And we need KTE initiatives, knowledge transfer initiatives to overcome potentially some of those constraints. So that's the structure we've adopted, and it's the same for all of the mitigation measures in section 4. Okay, so I'm going to go through how we model the protected urea mitigation pathway. So we start with the total. This is kind of the business as usual, no intervention. So this is the S1 without any mitigation. So you're looking at I'm only going to present the first and last year of the study period, just so I'm not going to bombard you with numbers, but they're all there in section 4. So total chemical N at the start and end of the period, and the profile of fertilizer. So you can see there, straight CAN and high CAN, low pK compounds are a significant contributor to the overall chemical N proportion. High CAN, high pK compounds less so. Straight urea is in the order of 50,000 tons, and we're starting from a very low base then with protected urea in 2021 at very little, a couple of tons basically. So the mitigation pathway is how do we change that profile of fertilizers. So under this is the assumptions we used in the mitigation pathway. So for straight urea, for protected urea, we're substituting, essentially we're taking out straight urea in 3 steps between 2021 and 2023. And from 2023 onwards, all straight urea is gone and substituted to protected urea. For CAN, we're substituting half of the straight CAN and half of the high CAN, low pK compounds, stepwise 10% per annum to 2025 and 50% thereon to 2030. So half of the CAN and all of the straight urea. We're also getting, how does that affect the overall aggregate level of fertilizers? Well, it's a slight reduction in the aggregate level because protected urea is better at N recovery, so we can reduce the overall chemical fertilizer level somewhat. But the main difference is the profile of fertilizers that are applied. So you can see there, the CAN has reduced in half essentially. The straight CAN and the high CAN, low pK compounds. We've maintained the high CAN, high pK compounds at their levels because we need the P's and K's for the soil fertility. The main difference is in the straight urea. We've essentially taken out straight urea, and you can see there that protected urea is now almost half of all chemical and applied by 2030. So that's the major impact of the mitigation pathway. So what effect has that change in fertiliser profile had on the overall mitigation or the abatement side? Okay, as Dominica has kind of outlined before, there is a bit of a conundrum here in terms of protected urea is 5 times lower emission factors than straight urea. That's a win-win, but it has higher emissions than straight can and can compounds. And the pathway is set out essentially to tackle greenhouse gases as well as ammonia. So by substituting protected urea for straight can and can compounds, we're actually increasing ammonia emissions from that portion of the pathway. So you can see this is how we've modeled it. So at the very top, we're seeing 6 kilotons reduction of substituting protected urea for straight urea. That's obviously a big jump, but we also have increased ammonia emissions from the can element essentially. When you combine the urea and the can element, you're still getting an overall reduction in the order of 3.3 kilotons in 2030, 3.1 over the average over the period. So that's essentially how we model the benefit side or the abatement side of the equation. Moving on to the cost side of the equation. Because protected urea is has better end-use efficiency, we can reduce the overall chemical N, the volume in volume terms. So we're getting a reduction in volume, which is volume effect. We're also getting a price effect. We're using constant prices over the study period, and protected urea is significantly cheaper than straight can and high can compounds. A little bit more austere than straight urea. But when you combine the volume and the price effect, and you cost in the baseline versus what the change is in terms of protected urea, you're actually reducing the aggregate fertiliser bill by 9.25 million euro. So it's a cost saving by implementing this mitigation pathway for farmers. So essentially, it's cheaper fertilisation strategy than the baseline. Okay, so when you put all those numbers together, so this is the mitigation year on year 2021 to 2030. You can see in 2030 it's 3.27 kilotons. The cumulative effect of that mitigation is 31 kilotons over a study period. The cost again in 2030 is a reduction in 9.25 million euro, a total reduction over a study period of 71.49 million euro. And when you put those two together, you're getting a cost effectiveness ratio of minus €2.30 per kg of N abated. So it's actually a cost negative measure. It's saving money for the farmer, and it's reducing ammonia. So it's a win-win. So I'm going to hand you back to Dominica for the results of the individual measure results, and she's going to talk you through the MACC graphs. Back over to you, Dominica.
Thank you very much, Cathal. Yeah, so Cathal talked you through an individual measure, and here I want to talk you through the outcomes of the whole analysis. So what you see here is a MACC graph. And basically, how do you read it? So there's 13 bars here representing the 13 individual measures. If you look at the left here, taking an example of the crude protein in the dairy cow diet, what you can see is the width of the bar represents the potential mitigation that we can get by adopting of the measure. And the height of the graph represents the cost associated with adoption of that measure. So whenever the bar is below the zero line, that means that it's saving farmers money. Whereas when it's over the zero line here, as the example of measures on the right-hand side, it means that it's costing money. And as you can see as well, the shape of the bars differ. So you can have mitigation, you can have measures that provide more or less mitigation and at a very different cost. Okay, so what you can see here is there's 6 measures on the left-hand side that are saving farmers money, and these are reducing crude protein content in the diet of pig and dairy cows. It's including clover in grasslands hordes, liming, changing over to protected urea, and covering stores, slurry stores on the pig side. Okay, so these are all kind of cost negative measures, which means straight away they're saving farmers money. There's 7 measures then on the left hand, on the left hand side, which are which represent a cost. therefore there might need to be some sort of mechanism to help with their adoption. And what's very clear from that graph and really stands out is the protected urea and less on the bovine side, as these two measures are very cost efficient, with protected urea being slightly negative and less on the bovine side being only slightly positive, introducing more cost. However, between those two measures, they can provide approximately 80% of our mitigation. So this is, this is a really kind of a powerful outcome of those two individual measures. So that's really the outcomes of the whole MACC analysis based on the S1 scenario, where you can see how the different measures compare against each other. And I'll pass you back to Cathal to show you what it means for ammonia emissions globally in the Irish context if we followed the adoption pathways of all those 13 measures, and how the emissions will look like into the future.
Thanks, Dominica. So, okay, so this graphic kind of brings it all together essentially. So, if we implement the 13 measures, as Dominica has very eloquently outlined, and we impose them on the S1, the S2, and the S3 activity levels, this is the level. This is the aggregate emission levels we end up with. Again, the red dots are our targets under the NEC directive, and you can see there from 2020, we're getting, assuming full mitigation of 13 measures, we're getting significant declines between 2020 and 2023. This essentially because a lot of the acclimatizing measures are front loaded, and we're seeing the effect early on, and we're getting after that. Then there's a leveling off. It's still declining, but it's leveling off from 2023 to 2030. So all of the measures dip below the 2020 target fairly soon after that. After implementation, towards the end, at the very end, 2030, that the S1 and the S2 are below our NEC directive target, and significantly so. Whereas the S3 is above the line. We're not meeting our targets. We're not meeting our NEC directive targets with the S3 level of activity. So in that scenario, to achieve targets, we'll have to engage with a different pathway or more mitigation or some alternative strategy. So I want to go through some caveats of the analysis. As ever, there are caveats. There are significant uncertainty around the activity levels. Brexit is in play with COVID-19, so it's really uncertain what the activity level is going to be, and that's what the FAPRI Ir model it's done a sensitivity analysis of 3 different high, low, and business as usual type scenarios, so you can get the spread, but it's very unclear as to where we're likely to be in that overall activity level spread. Look at the analysis assumes certain adoption rates. Some of them perhaps are quite challenging. The analysis assumes that we're getting all those adoption rates in a timely fashion to achieve the mitigation we need to achieve. There are efficiency gains. The analysis is predicated on efficiency gains, and it's also predicated where there are efficiency gains, the farmers will reduce their chemical N proportionately at farm level. So, for example, if you take example of trailing shoe, if the farmer goes out and uses trailing shoe, then he essentially has to reduce his chemical N on the back of all the N recovered by using trailing shoe. Otherwise, the efficiency won't be gained. So that's the big, I suppose, challenge is to get KT challenge is to get farmers to reduce their chemical fertiliser on the back of these mitigation pathways and the gains they will achieve. And just to note, look, there are potentially synergistic antagonist effects of some of the measures on other environmental dimensions, like greenhouse gases, and we've seen the protected urea one, as Dominique has outlined, potentially also water quality and biodiversity. So we have to assess the measures on different dimensions, but generally speaking, from literature, it tends to be more of a synergistic and antagonistic effect in general terms. Okay, so to conclude with some take-home messages. Look, we've explored 13 measures and there are significant overall abatement potential there. they're all predicated on improving nitrogen use efficiency and reducing chemical N. We have to get the chemical N down on the back of these pathways. There is a diverse range of abatement potential from one of the poultry measures, 0.8 kilotons, to the low emission slurry spreading up to 9 kilotons of abatement. And as the director said at the start, there are, and Amika showed in the graph, there are 6 measures that are cost negative or cost savings, which total 22 million euro, and there are 7 that are cost positive that total 33 million euro. So the net effect is cost positive 10 million euro. Look, if people take one thing away from this seminar, and sometimes we're accused, excuse me, sometimes we're accused of not giving clear messages from our research. If people take one thing away from this seminar, it's 80% of our abatement can be achieved by 2 mitigation pathways. It's low emission slurry spreading for bovines, and switch to protected urea fertiliser. And the protected urea fertiliser is actually a cost saving. It's a win-win. It saves farmers money, but it also reduces ammonia. And on the left side, okay, it's going to cost farmers some money, but it's at the lower end of the cost spectrum. It's €1.40 per kg of NH3 abated. So if we get those 2 measures implemented, we're 80% of the way there. And for people who are interested, that's the link to the full report. As Dominica said, all of the mitigation measures are set out in detail in section 4. All of the assumptions are set out there, so you can agree or disagree with our assumptions. We've put them out there to how we've modeled each of the individual measures. So on that basis, John, I'll finish up, and I think myself and Dominica are happy to try and answer any questions that people might have.
Yeah, thank you, Dominica and Carl, for that very clear explanation of what is a very complicated and detailed analysis that you've put together. We've got quite a number of questions come in already. We have something like 20 minutes left for questions, but I would encourage any of the attendees to put their questions up on the Q&A tab at the bottom, and we will try and deal with them as many of them as we can. The first one I think is probably for you, Dominica, and it's a question saying, can you just summarise the problems caused by ammonia?
Okay, so there's, yeah, as I said, John, there's kind of the twofold effects on the health effects and the habitats. So on the health effects, it basically causes respiratory health issues, especially when if ammonia kind of comes in contact with particulate matter and particulate matter pollution in the air. Then causes larger particles that can deposit into the airways. So that's on the health side. On the habitat side, what it can there's a range of effects that it can cause, but basically it can what it does is it deposits on the soil and on the ground and on vegetation, and provides it with, basically it's a nitrogen deposition, so it kind of fertilizes the ground and the plants in a situation where it shouldn't. So these are habitats that are normally known for very low a kind of level of nitrogen. So providing additional nitrogen from that deposition will change how the vegetation reacts, what kind of vegetation thrives in those environments. So what it might do is it might change the vegetation type. It might really impact on on growth of certain species.
Okay, thank you very much. There were a couple of questions on that. There may be a couple of things we might pick up on afterwards. We've got a few questions as well in terms of low emission slurry spreading. One question here is, how does the Irish inventory treat trailing hose compared to trailing shoe slurry spreading? The UK emissions factor states that trailing hose is half as effective as trailing shoe. Is the same assumption made in Ireland?
The same assumption is made in Ireland. However, at the moment, the inventory actually assumes 100% usage of splash plate, and the reason behind it is, there's been no data, activity data, on the use of the less methods in Ireland. So that's why we've been using splash plate all along. So on the back of, I think, the recent report from Cahill and his team, we are starting to get information on the level of the use of low emission slurry spreading in Ireland. So hopefully that might help with the adoption of capturing it in the inventory. But when it will be captured, it's the same situation similar to the UK, where trailing hose is half of the abatement potential of the trailing shoe. So that's correct. It's the same for us.
Okay, thanks, Dominica. Cahill, do you want to comment on how that information is being captured in terms of usage of less methods?
Yeah, up to now, John, we've no mechanism for trying to capture what's happening on the ground. So we published a report earlier this year, manure management report. It's on the Teagasc website. It basically said about covered 16, 17, and 18 years, and that about 4% of the aggregate slurry was being applied by low emission slurry spreading methods. So we have huge room for improvement there, obviously. And I'm just in the middle of generating 2019 results. I have seen, a significant jump in that even last year. So it's probably doubled from the 2018 to 2019. So the trend is one way. So it's encouraging that farmers are jumping on board the low emission slurry spreading.
Okay, thank you. And there's a question here that relates to the scenarios, which maybe just you could answer quite quickly. We've got questions coming in by the dozen. So we'll try and keep the answers short. From the graph showing trend analysis of the cow numbers and fertiliser projections, can we imply that the scenarios of hard and soft Brexit increase cow numbers compared to business as usual?
It's intrinsic in the model, John, but my understanding of how FAPRI works is that the dairy sector is less exposed to Brexit than the beef sector. So even in a hard Brexit, there's room for the dairy produce to go elsewhere and get relatively good prices versus the beef sector. So this means that the dairy cow numbers increase under the three scenarios, but the decline to various extents based on Brexit. But on the beef, they're being offset to varying or lessening extents by the hit the beef sector is taking in a business as usual versus a hard Brexit scenario, if that makes sense.
Okay, yes, thank you very much. Now I have a very hard question for you both. Could you explain, please, is the 31 kilotons reduction in ammonia from fertiliser, does it take into account the other measures if they've been adopted and resulting in increased end use efficiency? And I think that relates to how you calculate up the overall effects and in what order you apply the measures. So I know this is quite a complicated thing to explain, but
I might go first and Dominic come in maybe.
Yeah.
We modelled each of the measures individually first. So we've given the marginal abatement cost curve as individual measures, but the graph I presented at the end showing the S1 scenarios with full mitigation, that takes into account the interactions between, because as some of the measures are implemented, they interact with each other and you're getting less mitigation. And Dominique in the document has set a very eloquent diagram to show an inflow of how the measures kind of were implemented in sequence. And I will hand over to you, Dominique, to give a better explanation of that.
Yeah, maybe without going into too much detail, Cahill. So the way the measures work is, they follow the nitrogen flow model through the system. So, you kind of have the nitrogen flow through bovine, pig, and poultry sectors, and through fertiliser. They're kind of treated separately, and then they're interacted at the end, what Cahill was saying. So if you, for example, think about a cow ingesting certain amount of nitrogen in the diet, and then excreting that nitrogen, it goes through housing, storage, land spreading. And if at each or some of the steps we reduce ammonia emissions, we're holding on to more nitrogen. So ultimately, by holding on to the more nitrogen and using, let's say, low emission slurry spreading, we're increasing nitrogen use efficiency of that manure. And based on that, that, for example, that also goes into the savings in synthetic fertiliser. So all of those measures are first interacted and kind of implemented in an order, and that they kind of appear logically in that manure management flow. And from those we get nitrogen savings. And only at the very end, then we can switch the fertiliser measures. So in a way, the way the model works, protected urea is actually the last measure, where you're getting savings from all the other measures that kind of slightly reduce the fertiliser usage. And then based on that reduced fertiliser usage, then you also change fertiliser source. Hopefully that makes sense.
Thank you for that. I know it's quite a difficult part of the MACC, or the overall analysis in the MACC. I could perhaps recommend, if people want more detail, that they could perhaps contact you afterwards, perhaps having read the report or the relevant section in the report. Just moving on, there's a few questions about other potential mitigation measures that aren't mentioned in the MACC analysis, and some specific questions related to alternative land uses such as forestry or tillage, but also anaerobic digestion. And could you perhaps mention some of these other methods and why they aren't in the analysis?
Right, so will I maybe take that one, John? There's nearly two questions in one. One is on the measures that might appear in the MACC analysis in the future. And look, there's a whole section in the document outlining those. So without going into a huge amount of detail, there's research, there's ongoing research. So within the different timeframes, we're hoping to include different measures that will be applicable to Ireland, such as kind of smart housing and reducing ammonia emissions in housing, looking at farm-yard manures that we haven't looked at before. We've focused on slurry, using kind of topographical features, like for example, windbreaks and rows of trees, that stop ammonia from that longer range transport. So that's all outlined in the report in terms of the measures that might go in the future. As I said, we focused on category 1, so those really kind of tried and tested that can be easily implemented. In terms of kind of slightly different scale measures, like the kind of more landscape based and land use, that's coming at it from a slightly different angle. I appreciate that comment. The way the MACC analysis was carried out was using the EPA inventory model, and actually we're kind of very gratefully acknowledge the EPA and Bernard Hyde for providing that model. So the basis for the analysis was to use the same methodology as the EPA, so that we know straight away how those how the mitigation measures can be implemented and how they can be counted in the inventory. So what Cathal was said earlier, we do want to get that those mitigation measures counted in the inventory. We want to get the benefit of those, and we want those to be recognised.
Okay, thank you, Dominica. I think this is another one for you. You're not getting off very lightly. This question is, how far does ammonia travel? We've got a few questions relating to, I guess, the issues in the north and the south, and you showed the map, which had perhaps higher levels in the north than the south. So how far does ammonia travel? Is it very local, or can it travel significantly? And does this have implications for how we need to coordinate across the island of Ireland what we're doing?
Okay, so it depends, and the ammonia is treated as a long-range pollutant. So, it's treated that it can travel long distances. However, what we've seen and what we know from research is a lot of the time it actually deposits within a short distance rather than traveling those longer ranges. So it does very much depend on the condition, of the atmospheric condition, on the topographical conditions, how far that ammonia pollution will travel. So it's not an easy one to answer. And if anything, my research in a way is more focused on emissions than on the concentrations. and a postdoc working with me, David Kellahan, actually just finished a PhD on kind of concentrations and movement of ammonia. So he's another good person, and there's an EPA report just published there very recently. So that might be of interest in terms of more so ammonia movement.
Okay, thank you. And I'm going to ask this question anyway, although knowing how much time you've put in recently to putting in the ammonia MACC together, it might not be a very fair question. Are there plans to produce an integrated farm sustainability map so that you can look at the overall costs of implementation for all of the targets that we have? I'm sure you're enthusiastic to start another MACC straight away. Perhaps you'd answer that.
That's probably falling towards me, John. Yeah, I've started. I have a PhD student who's kicked off the process of trying to look at an integrated marginal abatement cost curve at farm scale. So I'm coming from background of water quality, and now I'm in the mitigation emission space. So I suppose I have some knowledge in trying to start that process. We could do with some funding. So if there's funders listening to the webinar in your next funding call, it'd be useful to have some resources to look at the whole spectrum and look at the mitigation across different dimensions and different scales. So the work has started, John, but it's not going to be delivered today or tomorrow.
Okay then. So many questions here now, I'm getting lost in them. Here's another one, perhaps a more technical or soil science one, so it's probably one for you, Dominica. Given that nitrogen types are all readily transformed in the soil, will the switch to protected urea not eventually lead to higher future losses unless the overall N load into the soil is reduced? I'm not sure whether that relates strictly to ammonia or whether it's nitrogen losses as a whole in terms of and nitrous oxide emissions.
Yeah. I'm not entirely sure I'm getting the question right, but if it is, I think it's really relating to nitrogen loading in general. So where we're increasing the nitrogen use efficiency on the back of a variety of measures in the MACC, we made an assumption, and yeah, it is a very big assumption that means to a reduction in synthetic fertiliser N. Because yes, otherwise you would be increasing your NUE and keep on adding the same amount of nitrogen. You would end up with more than what you need. You would end up with an excess. So I'm not sure if that was the question, if that's the answer to that question. And I think in terms of be it fertilizer and be it ammonia or another emission, it's general nitrogen use. So it really highlights that need for kind of integrated approach of, yes, we've looked at ammonia and we've previously looked at greenhouse gases, but we really need to kind of go into more integrated approach of looking at nitrogen in general, nitrogen cycling, and nitrogen will have impact on those, on those different environmental goods and bads.
Yeah. Okay. I think my understanding is that the analysis, if there is more of the nitrogen retained, ammonia is emitted very soon after application, whether it be in terms of artificial fertilizer or slurry. If the analysis shows that you retain more of that and it gets into the soil and can be used by plants, then your assumption is that you would need to apply less fertilizer in the first place, which I think answers that question. So there shouldn't be an overall increase in N loading to the soil.
I would agree, John. And just another question came in there is in relation to how likely are we likely to get those reductions on the back of efficiency gains. I suppose just answer that one is that in the mitigation emissions working group, we have all our KT colleagues in there, so they are aware of the challenges of trying to get this into our KT programs. And I guess I mentioned that the signpost farms are going to be set up, and with the raison d'etre of showing farmers, best practice and how we need to reduce our fertilizer on the back of that. So look, we have KT programs trying to be rolled out and working with farmers to try and get the fertilizer down and save the money.
Yeah. Okay, thank you. And we're running out of time very quickly. So just one further quick question in relation to the emissions factors. How do they depend on actual measurements? So are they, have you measured the actual emissions to come up with the emissions factors, or are they book figures, I think is the question.
Okay, so they they're book figures, but the book figures are based on measured values. So they either come from a standard EMEP book that covers emission factors when there's no national data, or from our own national research. So it's a combination, you know, and that's again outlined in Chapter 4 for each measure individually. So depending on the measure, we always provide the basis for the emission factors used.
Okay, thank you, Dominica. And thank you, Cathal, both for your presentations and for your excellent answering of the questions. I'd like to thank the attendees for all of their questions. Hopefully we covered most of them. I did try and amalgamate a few of them. But again, thank you for attendance. We are actually out of time, but just before we leave you, just to let you know that the next two Teagasc Research Insight webinars on the 21st of October and the 4th of November will be in relation to food and its interaction with gut bacteria. And then from the 18th of November onwards, there will be a series of these webinars related to land use and issues around land use. Okay, and you can see the details of the first or the next food webinar there on your screens now. So I'd like to thank you all for your attendance and to draw the webinar to a close. Thank you very much.